10,000 charging cycles. Not a lab projection, a certified result from CATL's own Tech Day, confirmed for 2026 mass production. Something the industry quietly gave up chasing a decade ago, written off as too heavy, too slow, too far behind lithium to ever matter again. You heard that right. A chemistry left for dead is now shipping inside real cars. That is not a footnote. That is a company betting its entire identity on the idea that one battery was never going to be enough. You know that feeling of watching your phone battery die a little more every single year until it barely makes it to dinner. This is the industry finally refusing to accept that as inevitable, and sodium is not even the strange part. What is coming next does not use chemistry at all. Stick around and hit subscribe, because by the end of this video you will understand exactly how China ended up 4 different ways ahead on batteries at once. For 30 years, lithium-ion has been the only real answer. Every phone, every laptop, every electric car on the road runs on some version of the same chemistry, and for a long time that felt like a settled question, the kind of thing engineers stopped arguing about. The ceiling was well understood, even if nobody liked saying it out loud. Push past roughly 250 to 300 watt-hours per kilogram in a commercial cell, and you start trading energy density for stability. Push the cell too hard in the cold, and range collapses, sometimes by a third, exactly when you need it most. Damage the electrolyte, and you're looking at thermal runaway, the industry's polite term for a fire that starts inside a sealed can and does not stop until the can is empty. Toyota, Samsung, and a string of well-funded Western labs spent decades and billions of dollars trying to engineer around that ceiling. Most of them are still trying. QuantumScape alone has burned through billions in venture funding, chasing a next-generation cell that still has not reached a customer's driveway. That is not a knock on the effort. It is a measure of how hard the ceiling actually was to move, and how little margin was left for anyone still working strictly within lithium's rules. Here's what most people get wrong about that ceiling. It was never really a chemistry problem, it was a monoculture problem. Lithium-ion became the only crop in the field, and the entire industry built its infrastructure, its supply chains, its factories, and its safety standards around a single plant that could still fail in a hard freeze or a hard collision. One bad harvest, and everyone downstream feels it. Samsung SDI and LG Energy Solution both spent the better part of the last decade chasing marginal improvements to that same basic chemistry, squeezing out a few extra percentage points of density a year while the fundamental ceiling barely moved. That is the wall Robin Zung was staring at in 2011, the year he founded CATL in a small industrial city in Fujian province with a bet that looked, at the time, close to reckless. Zung had spent years inside the battery supply chain before that, and he had watched the same failure mode repeat itself over and over. Whenever lithium prices spiked, whenever cold weather cut range, whenever a single cell failure made headlines, the entire industry had nowhere else to go. There was no backup plan, no second crop to fall back on. In 2016, with lithium carbonate still cheap and sodium-ion research offering no obvious commercial payoff, Zung pushed his teams to start developing a sodium-ion program anyway, diverting engineering time toward a chemistry most of the industry considered a dead end. Colleagues at the time reportedly treated it as a research curiosity, a hedge with no near-term use and no real budget attached to it. Zung's stated goal was not to replace lithium. It was to make sure no single chemistry could ever again hold the entire industry hostage the way lithium had. By the time he made that call, CATL had already grown into the largest battery supplier on the planet, which made the decision harder to justify internally, not easier. A market leader has more to lose from a distraction than a startup does. Diverting engineers, lab space, and capital toward a chemistry with no clear market was the kind of move that gets second-guessed in board meetings, not applauded. That decision sat mostly dormant for years, unfunded in any serious way, and easy for outsiders to forget entirely. But it did not die. And when the industry finally needed an alternative, it was already sitting on the shelf a decade ahead of schedule, waiting for the moment lithium prices or lithium's limitations made the wait worth it. What Zung could not have known in 2016 was that his sodium bet would turn out to be only the first of 4 separate wagers converging on the same problem. And the next one did not even use chemistry at all. Sodium-ion was announced quietly, almost apologetically, back in 2021, a lab curiosity from a company that already dominated lithium and had, on paper, no reason to bother. Analysts inside the industry treated it as a hedge, not a product worth watching closely. Western battery researchers largely dismissed it outright, arguing that sodium's lower energy density made it a dead end for anything beyond stationary grid storage, never something you would put in a car people actually depend on. Industry conferences treated the announcement as a curiosity slide, worth a paragraph in a trade newsletter and nothing more. Sodium sits directly below lithium on the periodic table, and on paper, that similarity should have made the chemistry easy to adapt. In practice, sodium ions are physically larger, which meant nearly every electrode material engineered for lithium simply did not work once you swapped the ion. They said the same thing about lithium-ion itself in the 1970s, when it was considered too unstable, too expensive, and too impractical to ever leave the laboratory bench. We all know how that ended. What the skeptics missed with sodium was the same thing an earlier generation missed with lithium half a century earlier. A technology's first version is never its ceiling, only its starting line, and dismissing the starting line as the finish is how you get blindsided a decade later. The program that followed involved a decade of steady, mostly unglamorous iteration. New cathode structures, better electrolytes, a shift toward materials that could survive extreme cold without the bulky thermal management systems lithium cells require just to function normally in winter. By 2025, CATL had a working sodium-ion line under the brand name Naxtra, supplying passenger vehicles and heavy trucks rated to function from -40 degrees Fahrenheit up past 158 degrees, a temperature range that would cripple most lithium packs long before it got that extreme. But the announcement everyone dismissed in 2021 was never really about sodium on its own. Here's where the story really begins, because sodium was just the first crack in a much bigger idea. The idea that the future of power was not one battery, but 4 completely different ones, each solving a problem the others could not touch. And the next one on that list does not look anything like a battery at all. Picture something with no charging port, no liquid electrolyte, and no chemical reaction happening inside it whatsoever. Picture something the size of a coin that generates a small, steady trickle of electricity for 50 years without ever being plugged in, refueled, or replaced, quietly outliving nearly every device it could conceivably power. That is Betavolt, a Beijing-based company whose chairman and CEO, Zhang Wei, unveiled the original version of this device in January 2024 to widespread skepticism about how something this small could ever matter beyond a novelty for a trade show display case. Here's the problem Betavolt actually set out to solve. Radioactive decay releases energy constantly and reliably on a schedule measured in decades rather than hours. But converting that decay into usable electrical current at a useful scale has always required either heavy shielding or bulky conversion hardware, neither of which fits inside a device the size of a fingernail. Betavolt's answer was to sandwich an ultra-thin 2-micron sheet of nickel-63 between 2 wafers of diamond semiconductor, the way you might sandwich a sheet of foil between 2 panes of glass, letting the diamond's wide band gap capture the beta particles the isotope naturally sheds and convert them directly into a stable, continuous current. Stack enough of those modules in series and parallel, and the output scales in a predictable, almost modular way, closer to building with bricks than brewing a chemical reaction. As the nickel-63 decays, it converts into stable, non-radioactive copper, which is part of why Betavolt describes the design as inherently safe rather than just shielded. The verdict is simple. This is a battery that outlives the device it powers. And Zhang Wei's team did not stop at the original coin-sized version. Their newest iteration, announced this year, delivers a 15.5-fold jump in volumetric power density over the original design, with 0 foreign parts in its construction and a working range from 100 degrees below freezing to 200 degrees above boiling, conditions that would destroy a conventional lithium cell in minutes. This is the same instinct Zhang had bet on with sodium 3 years earlier, just aimed at a completely different problem. Stop assuming there is only one correct way to store and release power and start treating every use case as its own engineering question rather than forcing every application through the same lithium-shaped door. But longevity was never the whole equation. A battery that lasts 50 years is worthless at scale if it cannot produce more than a few microwatts, and scaling real power output required solving a problem that sodium and nuclear power both sidestepped entirely rather than solved. Somewhere in Guangzhou, a much more familiar-looking battery problem was being attacked from the opposite direction. Solid-state batteries have been the industry's most coveted, most stubbornly unsolved prize for the better part of a decade. the technology every major automaker keeps promising and keeps delaying. Toyota alone has pursued it for over 20 years. The theory has always been simple. Strip out the liquid electrolyte that makes lithium-ion cells flammable, and you get a battery that cannot catch fire, holds dramatically more energy per kilogram, and degrades far more slowly over its lifetime. The practice has been the opposite of simple. Every leading approach, sulfide, oxide, polymer, halide, carries its own deal breaker. Sulfides conduct ions well, but react violently with air and moisture, turning manufacturing into a logistical nightmare. Oxides are stable but brittle, prone to cracking the moment you try to manufacture them at any real scale, which is exactly where most competitors have stalled for years. Polymers solve the brittleness, but only conduct ions efficiently at high temperatures, which defeats the purpose in a car sitting in a cold parking lot overnight. The solid-state race has essentially been a four-way sprint where every runner has a different injury and none of them has crossed the finish line first. Here's the detail that puts everything into perspective. Greater Bay Technology, a battery startup backed by China's GAC Group, took a fifth path nobody else was seriously pursuing: a proprietary deep eutectic composite electrolyte, combining materials the rest of the industry had never seriously tried pairing together in a single cell. It sounds like it should not work. Mixing multiple material systems into one electrolyte usually multiplies your failure points instead of eliminating them. That is exactly why it does. In 2026, jack-back cells reached energy densities between 260 and 500 watt-hours per kilogram, roughly double what a conventional EV pack delivers today, enabling related test vehicles to travel 745 miles on a single charge, farther than most drivers cover in a week. Greater Bay has already filed more than 50 patents covering the electrolyte materials and the manufacturing process behind them, and GWH scale production is targeted before the end of this year. This is the exact fork every major Chinese battery maker, CATL included, now faces. Keep refining known chemistry, or gamble on an entirely different material architecture and risk years of sunk R&D. Pilot data is one thing. Putting that architecture inside a car that has to survive a crash, a pothole, and a decade of daily abuse is an entirely different problem. And the industry's next move was not a new material at all. It was to stop treating the battery as something you bolt into a car in the first place. For as long as electric vehicles have existed, the battery pack has been treated as cargo. A heavy, sealed unit bolted beneath the floor, structurally inert, contributing nothing but weight to the frame around it, while the actual chassis did all the work of holding the car together. Engineers accepted that trade-off because separating the battery from the chassis made it easier to service and safer to isolate in a crash. For most of the last 15 years, that logic was treated as settled, the same way lithium sealing was treated as settled, and very few engineers were willing to bet their careers on tearing it up. Few people who write about electric vehicles ever get to this part of the story. That trade-off was never actually necessary, just convenient. Picture a car that is not powered by a battery hidden underneath it, but powered by the floor itself. The very structure holding the cabin, the seats, and the passengers all at once, doing double duty as both power source and skeleton. That is what CATL's cell-to-chassis integration, now in its second generation, and BYD's Blade battery both do. Instead of bolting a battery pack into the chassis like furniture bolted into a house, the battery cells themselves become the house's foundation, load-bearing and structural rather than just along for the ride. The engineers who worked on early structural battery prototypes will tell you this detail rarely makes it into public coverage. Getting cells to bear crash loads without compromising safety required rethinking the internal architecture of the pack from the ground up, not just gluing a conventional pack to the frame and hoping the math worked out. The combined result of that redesign was a number so aggressive that BYD reportedly required a second internal verification pass before anyone was willing to publish it externally. And that number is exactly where the story was always headed. Here is the honest picture. BYD's Blade battery passed 500 flash charging cycles, simulating 15 years of real-world daily use without losing structural integrity or measurable capacity. During nail penetration testing, driving a metal spike straight through a live cell, the industry's harshest and most feared abuse test, the pack produced no fire, no smoke, and no explosion. 15 years of wear, compressed into a lab result measured in a matter of weeks, and the structure held up every single time it was tested. That is not a marketing claim. That is a certified outcome from standardized abuse testing that the entire industry now treats as a baseline expectation, rather than a stretch goal reserved for press releases. Nail penetration failures used to be the single most common cause of headline-grabbing EV fires, the exact scenario every battery engineer privately dreaded. Watching a pack absorb that test 500 times over and still hold its shape is the kind of result that changes what regulators are willing to certify next. Here is the honest trade-off underneath all four of these stories. Sodium-ion still trails lithium on raw energy density. Solid-state production remains a year or more away from dashboard-ready vehicles at true scale, and nuclear batteries remain stuck at the microwatt level, nowhere near powering an actual car engine. None of these four breakthroughs alone solves electrification, and treating any one of them as a silver bullet would be exactly the kind of overclaiming this story is trying to avoid. Together, they are the first real evidence that the single chemistry era is already over. For Robin Zing, this is the moment his 2016 bet stops looking reckless and starts looking prophetic. He did not fund sodium-ion research because he somehow knew nuclear batteries, solid-state cells, and structural packs would all mature in the same 5-year window. He funded it because he refused to let one chemistry hold the entire industry hostage the way lithium once did. And 4 completely independent teams, chasing 4 completely different problems with 4 different toolkits, ended up proving him right anyway. If any of that surprised you, the next part of this story is going to be even harder to believe. Hit subscribe now so you are there when we cover it. None of this stays confined to one factory or one country's roads. The problem these 4 breakthroughs are chipping away at, range anxiety, cold weather degradation, thermal runaway risk, and the industry's total dependence on a single raw material supply chain, is a global engineering problem, and the response is becoming a global standard whether or not any single country intended it to. In September 2025, CATL's sodium-ion cells became the first in the world to pass China's GB 38031, the 2025 safety requirements for electric vehicle power batteries, a certification international automakers and suppliers are already using as a reference point when qualifying their own next-generation cells for their own markets. Automotive OEMs, grid-scale energy storage operators, and even aerospace and medical device manufacturers eyeing Betavolt's isotope batteries for remote sensors and implants are all now recalculating what the word battery even means for their sector. Adopting any of these 4 technologies at scale is genuinely hard, and nobody in this story is pretending otherwise. It requires requalifying entire supply chains, rewriting battery management software from the ground up, and retooling manufacturing lines that were built around a single chemistry for decades and are not easily converted. For a mid-sized automaker, that retooling can cost more than launching an entirely new vehicle platform, which is exactly why most manufacturers are moving in stages rather than switching chemistries overnight, phasing in sodium or structural designs on select models before committing an entire lineup. Here's the historical parallel worth remembering. Lithium-ion itself was dismissed as an unstable laboratory curiosity throughout the 1970s, considered too dangerous, too expensive, and too impractical to ever leave research benches for consumer products. It took roughly 2 decades for that curiosity to become the default power source for nearly every portable device on Earth, from laptops to power tools to the phone in your pocket right now. Nobody writing about batteries in 1985 was predicting that outcome with any confidence, which is worth remembering the next time an unproven chemistry gets dismissed as a niche. The limit on any of these 4 technologies was never ambition. It was material science, manufacturing yield, and time. And all 3 are now visibly closing faster than most of the industry expected. If you made it this far, you now understand more about the actual state of battery engineering than most people who cover this industry for a living. What was actually proven across these 4 stories is not that any single battery won the race, and the video is not arguing that it should. It is that the decade-long assumption, one chemistry, one architecture, one approach for every use case on the planet, has quietly collapsed under its own weight. Sodium handles the cold and the cost. Nuclear isotopes handle devices that can never realistically be recharged. Solid-state chemistry chases raw energy density most aggressively. Structural integration turns the battery into the vehicle itself, doing 2 jobs at once. None of these 4 approaches was guaranteed to work when the research began, and none of them came from the same lab, the same founder, or even the same underlying science, which is exactly why 4 of them landing in the same 5-year window matters more than any single spec sheet could, and more than any one company's marketing budget could manufacture on its own. Robin Zung built CATL on the belief that no single bet should ever be the whole strategy, and 4 unrelated breakthroughs converging in the same 5-year window is the clearest evidence yet that he was right to spend a decade waiting for the rest of the industry to catch up. And if the sodium story is the one that stuck with you most, I have already gone much deeper on exactly how CATL's Naxtra program pulled that chemistry back from the dead. That video is worth your time if you want the full picture behind today's opening number. If this changed how you think about batteries, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Which approach do you think actually wins for daily drivers? A structural battery built into the car's own frame, or a modular pack you can swap and upgrade independently the moment something better comes along? I read every single one, every time. See you in the next one.